Uh, and with that, I'm very happy to introduce our speaker today, Dr. Federico Galetto from Cornell University. So Federico's research has been focused on the use of deformation data to examine volcanic unrest and resurgence, and has had the opportunity to work on many different volcanoes around the world. He completed his PhD at Roma Tre University, followed by a short postdoc at the Etna Observatory with INGV, investigating magma propagation mechanisms, before moving to Cornell University, where he's been ever since. So he'll be talking to us today about some of his more recent work that he's been doing using high-resolution remote sensing data to measure topographic change at volcanoes, which sounds really interesting to hear about. So I'm going to hand it over to you with that, Federico. So whenever you're ready.
Yeah, thank you very much, Edna, both for the introduction and for inviting me to this webinar, where I can have the opportunity to share some of my recent results about the application of high-resolution remote sensing data to measure topographic changes in volcanoes, in which I'm going to show you both some success and challenges that we had and possible future perspectives. So, as you know, volcanoes are very dynamic systems that frequently and sometimes significantly can change their topography. So these topographic changes can be both positive, like in this case with the extrusion of a lava dome at St. Helena, or negative due to erosional and mass wasting processes, like, for example, observed at Zupanowski with the collapse of one of the craters. So quantify these topographic changes in volcanoes is very important for several reasons. First of all, to calculate the volumes of the erosional processes, but even more important, the volume of the erupted volumes, which provide us the sites of eruptions. This is particularly important, especially for effusive eruptions, because we know that at a global scale, lava is usually the main subaerial erupted products. But often the impact of lavas on the sites of the eruptions is underestimated, because many global databases, like the Global Volcanism Program, usually use scales to quantify the sites of eruptions, like the VI, which is a scale that quantifies the sites of eruption from the volume of explosive products, and therefore it's valid only for explosive eruption. So, for example, I show you the VI associated to all the eruptions by the Global Volcanism Program from 1980 to 2019, while here I show you the corresponding magnitude, where the magnitude is another scale to quantify the sites of eruptions, from which the sites is quantified from the total mass of the volcanic products, including lava. And you can see that there is a strong increase in magnitude 3, 4, and 5 eruptions just because the presence of lavas. And another important thing is that if it's possible to quantify topographic changes over the time, it's possible to quantify the eruption rates, that with important implication in the evaluation of volcanic hazard. For example, we know that volcanoes with a growing lava dome, which is quite common in arc volcanoes, often when we observe a sudden and strong increase in the extrusion rates, this is a precursor of a violent explosive eruption, as observed recently at La Soufrière San Vincent, but also multiple times at Merapi volcano in Indonesia. In addition, if it's possible to quantify topographic changes, it's possible to update the digital elevation models used to evaluate the scenarios of future volcanic hazards, such as the location of future pyroclastic density currents, lava, and lava flows. Another important thing is that topography plays a main role in determining the stress field of a volcano, and therefore changes in topography will lead to changes in the stress field, affecting the location of future eruptions. And finally, having updated high-resolution DEM is very important also to process at full resolution the satellite data, like, for example, InSAR data. And a powerful tool to monitor topographic changes at volcanoes at a global scale comes from satellites data, because satellites acquire data worldwide And this is an important thing because, for example, we know that UAV system or airborne system can have also resolution higher than satellites data, but they acquire data only at a very local scale. So satellites provide us global data sets, and from some of the satellites data, like radar data by using InSAR technique and optical data by using stereophotogrammetry, can be used to derive digital elevation models that can be used to study topographic changes in volcanoes from differencing DEM acquired in different dates. So among the available data sets of digital elevation models derived from satellites data, there are the lower resolution database, which are open source, like the SRTM and the ArcticDEMs, which are time-stamped, and some other database which are not time-stamped, like the Copernicus one. Then there are mid-resolution DEM, and what it is important for us today, there are high-resolution satellites data, like the bistatic TerraSAR-X TanDEM-X data, or the Pleiades data, or Maxar data, that can be used to derive high-resolution DEM, which is the focus of this presentation today. And in particular, I want to show you some success and challenges that we had using high-resolution DEM to study topographic changes in volcanoes. So with the first part of the presentation that will be dedicated to topographic changes from InSAR by using bistatic TerraSAR-X TanDEM-X data. The second part of the presentation will be dedicated to the application of EarthDEM and ArcticDEM, which are derived from optical data to study topographic changes. And then the last part of the presentation, I will show you some possible combination of high-resolution DEM with other remote sensing data to improve the volcano monitoring. So as for topographic changes from InSAR, we focus our attention on the bistatic pairs of data of the TanDEM-X TerraSAR-X constellation. In this constellation has the characteristic that allow to acquire two radar data of the same area at exactly the same time, one data acquired by the TerraSAR-X and the other one by the TanDEM-X satellites. And the fact that the two radar data are acquired at the same time allowed us to simplify the equation of the interferometric phase. And with the normal InSAR processing, it's possible to isolate the signal of topography from the other signals. And to do this, we use the modified routine of ICE software that allowed us to directly quantify topographic changes with respect to a reference DEM that we used in the InSAR data processing. And even though the bistatic data are not an open source database, they have been extensively used to study topographic changes in volcanoes so far, showing a lot of success in detecting volume changes related to different kinds of volcanic products, like, for example, lava flows or pyroclastic density currents. On the contrary, EarthDEM and ArcticDEM are high-resolution DEMs with a resolution of 2 meters, which are derived from optical stereoscopic Maxar satellites imagery, with ArcticDEM that covers all the regions with a latitude higher than 60 degrees north, while the EarthDEM covers only some regions with a latitude between 60 degrees south and 60 degrees north. And the interesting thing for us is that for the regions covered by these DEMs, we have multiple DEMs acquired over the time. Therefore, they allowed us to make multi-temporal analysis. However, these DEMs are derived from optical data with stereophotogrammetry. Therefore, often they show these translational and rotational offsets that need to be corrected before using them. And to do this, we co-registered these DEMs with respect to a reference DEM using the DEM-correg software. Even though these data sets are characterized by a very high resolution, just few volcanoes have been analyzed with ArcticDEMs, showing a good success in detecting topographic changes. So we made an in-depth analysis on the application of these data sets to study volcanoes. And the first analyzed volcano was Raung, placed in the easternmost part of the Java Island in Indonesia. This volcano experienced two lava flow eruptions, and for which we have both EarthDEMs and bistatic TerraSAR-X TanDEM-X data. So as for the first effusive eruptions occurred from 2014 to 2015, this eruption was characterized by the extrusions of lavas that partially filled the caldera floor of Raung, and by the significant growth of the intracaldera cone. So for this eruption, we have pre and post-eruptive EarthDEM, and by differentiating this EarthDEM, we calculated the topographic changes of about 40-60 meters in the caldera floor and of more than 100 meters in the area of the intracaldera cone. And thanks to the high resolution, we achieved to see almost all the lobes of the lava flows and also the channels. For this eruption, we have also the bistatic TerraSAR-X TanDEM-X data that we achieved to process at full resolution, so thanks to the pre-eruptive EarthDEM. And so you can see that we calculated the changes from bistatic data that are very consistent with those obtained by EarthDEM's differencing. Especially in the area of the caldera floor, while there are some differences in the area of the intracaldera cone, first of all, because we lost coherence in most of the area of the intracaldera cone. And then we have some areas like this one, in which we have where the topographic changes are very consistent with those from EarthDEM's differencing, while there are areas like this one at the base of the intracaldera cone, where we have some important differences, and we think that those are related to geocoding errors, because we see that the position of the intracaldera cone recorded by the bistatic data is shifted with respect to the position of the intracaldera cone recorded by the post-eruptive EarthDEM, and probably we think that this shift is not real but just related to geocoding errors. Then we also process the same bistatic data by using as a reference DEM, the lower resolution DEMs, in particular the ArcticDEM and the Copernicus one. Before using the Copernicus DEM, we changed the vertical datum from the geoid to the ellipsoid to be consistent with the vertical datum of the bistatic data. And here you can see that when we used the SRTM as a reference DEM, we significantly lower estimated the topographic changes of about 60-50%, while on the contrary, when we used the Copernicus DEM as a reference topography, we properly calculated the age changes with the age changes that are very consistent with those that we obtained by the differencing EarthDEMs. So the reason of why SRTM lead to a very wrong estimation of the topographic changes is probably due to the fact that inside the caldera of Raung, SRTM, it's very, very noisy. We have very important differences in the data recorded from one pixel to the nearby one, and probably this affected the InSAR data processing. While as for the 2021 eruption, it was characterized by lava flows in the north area of the caldera and by significant growth of the intracaldera cone. We processed at full resolution the post-eruptive bistatic data by using as a reference DEM, the 2018 EarthDEM, and we calculated the age changes of about 8-20 meters in the caldera floor, and of more than 100 meters in the area of the intracaldera cone, even though also in this case we lost coherence in most of the area of the cone. Other challenges with the bistatic data have been observed at Erde volcano, which is an hotspot volcano placed in the southern Indian Ocean, close to the Antarctica. And we see that with the amplitude, the geocoded amplitude data from the bistatic data, we achieved to map very well the growth of the lava flow during the time. But when we calculated the age changes with respect to the Copernicus DEM, we got negative age changes, and this is because the height of the glacier melted by the lava was higher than the thicknesses of the lava, generating overall negative age change. So it was possible with this data to map the area of the flow, but not the thicknesses and the volume. And something similar has been observed at Kilauea volcano, because in some areas the lavas destroyed very thick forest, and since the thicknesses of the tree were much higher than the thicknesses of the flow, in most of these areas they got negative changes. Then moving to the EarthDEM, ArcticDEM dataset, we know that so far only a few volcanoes have been analyzed with this data. So we started here in Cornell a big project with an in-depth investigation of the success and challenges of applying EarthDEM and ArcticDEM to detect topographic changes in volcanoes by analyzing the topographic changes from many different volcanoes with different volcanic activity. And this was possible also thanks to the research projects of a summer student and an undergraduate here in Cornell, which processed some of this data. So here I don't have time to show you all the results that we got, so I just show you a selection of the results to focus the success and challenges in using this data set. So starting with Fernandina volcano, which is in Galapagos, which experienced 3 lava flow eruptions from 2017 to 2020. And we see that in two of these eruptions, the 2017 and the 2020, occurred in areas where we found an unusual, very low signal-to-noise ratio that was never observed in the other EarthDEM and ArcticDEM that we processed. However, as for the 2017 eruption, we achieved to map very well whether each lava flows because they are characterized by high thicknesses, much higher than the vertical resolution of these data sets that we estimated to be in the order of 0.52 meters, very consistent with previous estimation. While as for the 2020 eruption, which was characterized by very low thicknesses, with average thicknesses of 1.5 meters, you see that especially in the areas with which are very noisy, we completely lost the signals of the lava flow, also because in these areas lavas have a thicknesses lower than the vertical resolution of these data sets. Fortunately, in all the other ArcticDEM and EarthDEM that we analyzed, we found a much better signal-to-noise ratio that allowed us to properly map and quantify the age changes of many kinds of volcanic products. Like, for example, here at Pavlov volcano in Alaska, we mapped for the first time the thicknesses of the 2013 and the 2 lava flows erupted in 2014. But we were able also to map a lot of other kind of volcanic products, like, for example, the 2013 eruptions produced a huge amount of sputters that accumulated both at the top of the crater and along the north flank of the volcano. And you see that we got indeed positive topographic changes that allowed us to quantify the volume of the sputter cone. Other unique signals detected from ArcticDEMs come from Cleveland volcano in the Aleutian Islands. This volcano has a narrow crater inside which it experienced repeated cycles of lava dome growth and destructions, with the cycles that lasted from few weeks to few months. And these lava dome usually are very small, with diameters between 40 to 80 meters usually. So they are very difficult to be mapped with low resolution DM, while the high resolution of ArcticDEMs provide us both the correct geometry and the correct height of these small lava domes. Of course, ArcticDEMs can be used also to map the topographic changes related to the biggest eruptions. For example, at Kizimian volcano in Kamchatka, it experienced a very big eruption from 2010 to 2013. For this eruption, we had only post-eruptive ArcticDEM, so we calculated the topographic changes with respect to the SRTM acquired in 2000. And you see that we obtained 8 changes and volumes that are very consistent with the previous estimations. But the interesting thing is that this eruption caused also the formation of a new lake. And since the ArcticDEM, the Maxar data from which our ArcticDEM is derived, were acquired in period where the two lakes were completely frozen. It was possible to extract the topography from the lakes. I think that would be not possible if the water was melted. And so we calculated an height of the lake of about 37 meters. Which is interesting because from field data, 1 year after the formation of the lake in 2011, it was estimated an height of the lake of 30 meters. So this implies that in these 11 years, the lake increased its level of about 7 meters, which is very consistent with the increase in the surface of the lake observed from optical data. And then we can also observe and quantify the larger sector collapses, like, for example, in 2015, one of the 4 craters of the Zupanowski volcanic complex collapsed, and we calculated that about 60 million of cubic meters were removed during this collapse. Then in Kamchatka, there are 3 volcanoes, Shevelus, Beziamian, and Klyuchevskoy, that are continuously erupting, and for which we have time series of ArcticDEM from 6 to 10 years. So we achieved to map the time series of topographic changes over the time. Now I don't have time to show you all the results, but it's important to show that we achieved to map also the largest deposits like this pyroclastic density currents, but also interesting signal. For example, thanks to the high resolution, we can study at a very high resolution both the erosional and the depositional process in the 2 scars at the top of the volcano. And another interesting thing is that Shevelus in 2020 experienced a spine extrusion at the top of the lava dome, where spine is the extrusion of this mass of very viscous and almost solidified mass of magma. And we had 2 ArcticDEM that were completely cloud-free, acquired during the spine extrusion. So you can see that the spine is not very big here at Shevelus, with a length of less than 300 meters and a width of less than 150 meters. And by differentiating these 2 ArcticDEMs, we achieved to map the growth of the spine occurred over this month, which is a very interesting result that would be not so easy to get from low resolution DEM. Other interesting things is that thanks to the high resolution, we achieved to quantify the accumulation of pyroclastic density currents and volcanic clastic deposits inside the narrow river valleys. We have to say that you need to pay some attention in quantify topographic changes inside the river valley, because often we see that inside these narrow valleys there are artifacts, but in these cases we checked the pre- and post-eruptive DMs, and they were artifact-free in these areas, so we can use them to map these topographic changes. At Klyuchevskoy, we achieved to map all the and to quantify the volumes of all the lavas erupted from 2012 to 2022. And among these lavas, there are some that are very interesting because, for example, we achieved to map this lava flow and also this other lava flow, which have a very, very low volume. But thanks to the resolution of this DM, we achieved to map them, which is important because, for example, in this case, this lava flow has a width of less than 50 meters, and we achieved to map it very well. Another thing is that in 2020, we had a cloud-free ArcticDEM, which show the new cinder cone just generated from the Strombolian activity. And from this DM, we achieved to map both its geometry and its height. But of course, there are also some limitations in using ArcticDEM to quantify topographic changes. For example, at Beziamian in Kamchatka, this volcano experienced in March 2019 is medium explosive eruptions, VI3 eruption, which generated both pyroclastic density current, ashfall deposits, and LAR, and surge. And you can see that by differentiating ArcticDEM acquired a few months after, and from another one acquired a few years before the eruption, Of course, the biggest signal is related to the growth of the lava dome mainly occurred before this eruption, but all the other signals are associated to the products erupted by the March 2019 eruption. And we achieved to map very well the main pyroclastic density currents and the large deposits inside the C-shaped valley of Bediamiani, while outside the C-shaped valley, we achieved to map and quantify the changes only inside the valleys where pyroclastic density currents are thicker, while we do not achieve to quantify the changes in most of the other places. In part, this is due to the fact that when the snow melted, part of the asphalt deposit were washed away. But the other reason is that probably the thicknesses of these deposits are in these areas lower than the vertical resolution of ArcticDEM, and therefore the ERT fuel could be detected. Something similar has been observed also at Pavlov, which experienced a VI3 explosive eruption in 2016, but we do not observe any clear signal that is directly related to the accumulation of asphalt deposits. Also, Raung, before the two lava flow that I showed you, it experienced repeated VI1 and VI3, VI1 and VI2 explosive eruption, but from the bistatic data, we do not achieve to map the tephra deposits. The only interesting thing is that one of the bistatic data, this one, was acquired the day after one of these small explosive eruption, and in this case, we had a loss of coherence in these areas, which might be the area of accumulation of the tephra. Of course, in the presence of the largest explosive eruptions, like a VI5 eruption or higher, they generated much thicker asphalt deposits that can be detected with this DEM. For example, the Puyi Cordon Kaul VI5 eruptions. For this eruption, another postdoc here in Cornell, Diego Lobos Lillo, generated from the bistatic data both pre and syn-eruptive DEM, and by differencing this DEM acquired before and after the end of the explosive phase, you see that we can map very well all the tephra deposits, which close to the eruptive vent were thicker than 10 meters, and then they decreased their thicknesses, but remain higher than the vertical resolution everywhere. And finally, it's also important to combine topographic changes from this high resolution DM with other remote sensing data to improve the volcano monitoring and the volcano understanding, especially for fully monitored and studied volcanoes, as for example, Semeru, which is placed in Java Island. This volcano is a persistently erupting volcano, so with the activity that is mainly dominated by strombolian activity that generated abundant lavas within the southeast scar. Sometimes the strombolian activity is interrupted by more violent volcanic eruptions, as observed, for example, on December 2021, with the volcanic eruptions that generated the pyroclastic density currents, which eroded significantly the scar and generated a huge amount of layers that unfortunately also caused some fatalities. So Semeru is definitely one of the most dangerous and active volcanoes in Java, but it's very poorly monitored and studied. So we start studying this volcano with EarthDEM. So we have EarthDEMs acquired in 2014 and 2020. So over a period where there was no erosion along the scar, but with the activity that was dominated only by the fusion of lavas, and therefore by differentiating EarthDEMs, we obtained the edge changes and the volume of these lavas, which we estimated to be of about 44 millions of cubic meters. And then we also analyzed the thermal anomalies automatically detected by Mirova by Mirova system, which automatically detect thermal anomalies as volcanic radiative power, VRP, from WIRTS and Moody's data. You can see that by investigating the full-time series of Mirova data, we see that Semeru was continuously characterized by moderate to high VRP anomalies, and we checked, and all these anomalies were directly related to the lavas. So we converted the VRP into the VRI, which is the volcanic radiative energy. And here I show you the cumulative curve of the VRI. With the VRI, which is an important parameter, because previous studies show that in some volcanoes, not in all, but in some of them, there is a direct relationship between the VRI and the volume of lavas erupted, with these two parameters that are related by these parameters, the CRAD, which is directly related to the composition of the magma. So this relationship is valid for some volcanoes, but not for all volcanoes. For example, all the volcanoes here in black, this relationship is not valid, mainly because they show a very important excess degassing. However, at Semeru, we know very well both the volume of lavas erupted from 2014 to 2020 from EarthDEM and the VRI from Mirova. So we see that it is a volcano for which it exists a relationship between these two parameters, for which we can precisely calculate the CRAD parameters, which is consistent with those of the other intermediate composition volcanoes and somehow also with the basaltic composition volcanoes, because Semeru has a basaltic andesitic composition, so it's more or less in between. And from the calculated CRAD, it was possible to calculate the erupted volumes of lava also for the two periods not covered by EarthDEM. So even though the volumes estimated from VRI have associated a very high error of about 50%, however, they provided us a first order estimation of the volumes of lavas erupted at Semeru from 2000 to present, which was of about 0.2 cubic kilometers. And in addition, it is important because with the CRAD right now, it's possible to directly have a first order estimation of the volume of lavas erupted in near real time from the Mirova database. In addition, the data also show that suggests that Semeru is experiencing a steady state activity. And then we analyzed the deformation data by processing InSAR data, in particular the Sentinel-1 data from 2014 to 2023. And we observed that from 2014 to mid-2021, the volcano experienced a very small subsidence focused around the scar, with negative line of sight displacement of about 14-16 centimeters, while the higher values detected in the lower part actually are not through value of deformation, because they match very well with the lavas in place just a few days, a few weeks before the acquisition of the Sentinel-1 data, and therefore probably they reflect the thermal contraction and cooling of the lavas. Another interesting thing is that previous authors suggested that the whole flank of Semeru volcano is experiencing a gravitational sliding. But the fact that the intensity and the magnitude of the descending and ascending data is quite consistent, especially from 2014 to 2020, suggests that probably the observed deformation is not directly related to the lateral spreading of the volcano. So we modeled this the observed deformation by using a boundary element method implemented in the DEF-Volca software. Before modeling the data, we removed the points above the lava flows. And the important thing of this software is that it allowed us to include also the effect of topography on the deformation, which is very important at Semeru, which has a very important and steep topography. So the results converged through a subhorizontal and very shallow source with a volume loss of less than 1 million of cubic meter. This is important because it's 2 orders of magnitude lower than the volume of lavas erupted over the same time span. So this large discrepancy cannot be directly explained only with compressibility of the reservoir. So we thought that the geodetic source actually it's not a magmatic source, but it's just an hydrothermal reservoir, which could be consistent with the fact that Semeru sometimes experiences phreatic and phreatomagmatic explosions, or could be just an ephemeral magma reservoir, but it's not the main source of magma, with most of the magma that probably is provided by deeper reservoirs, which do not produce any deformation detectable with InSAR data. So we can say that in conclusion, from our analysis of resolution DMs to detect topographic changes, we see that they have a very high potential for volcanology because they allow us to both large and small topographic changes. And the important thing is that both bistatic data and ArcticDEM EarthDEM allowed us to build a time series of topographic changes, which is extremely important to study very dynamic systems like volcanoes. And the other important thing is that these topographic changes can be combined with other remote sensing data to improve both the volcano monitoring and the understanding of the volcanic activity, which is important, especially for poorly monitored volcanoes and poorly studied volcanoes. Of course, unfortunately, there are also some limits because ArcticDEM, among the 3 datasets that we used, is the only one that is open source, while the other 2 are restricted. All these high resolution DM are able to detect age changes of about higher than 0.52 meters, which is the vertical resolution of these datasets. In general, this is a very good resolution, but we know that there are small ashfall deposits related to the minor explosive eruption that usually generates deposit with lower thicknesses, which cannot be detected with this high resolution DM. As for the bistatic data, in the steep areas, they are affected by layer and foreshortening effects, as well as often by loss of coherence, which prevent the possibility to detect topographic changes in these areas. And we have seen that also if you process bistatic data with a very noise reference DM, you can lower estimate significantly the age changes. While as for the ArcticDEM, they come from optical data, and therefore they are often affected both by clouds and by other kind of artifacts, which prevent the possibility to use those DMs in the areas affected by these errors. And so if you are interested, this is the list of the articles, of my articles from which I took the data that I showed you. And this is the list of the other articles from which I took all the other images. And before concluding, right now we have opened a special issue on Bulletin of Volcanology, where we are collecting articles that use remote sensing data to study volcanoes. So if you are working on these topics and you would like to send a contribution, we would very appreciate it. And so thank you very much.
Thank you, Federico. It was a really interesting talk. It was great to see all the different examples of the different processes that you were able to capture. I'll just remind everyone that you can add questions into the Q&A. I think they've got that message because there are quite a few already in there. So I think you should be able to see them as well, Federico.
Yes. So I can start.
Yeah,
okay, you can
out to you and then you can answer them. So the first one we have is from William Harwood, which says, fantastic talk. For some of the geomorphological applications, 10 centimeter resolution DMs data has been desired. Are you aware of any such kind of DEMs? I think everyone would love high.
Well, it would be great. I think that kind of vertical resolution, it's not possible from the present satellites data, but maybe it's possible from UAV system, I think. I'm not an expert because I've never used it, but definitely they are characterized by an even better spatial resolution. Therefore, I think that they could be characterized also by a better, smaller vertical resolution. So yeah, maybe not from satellites, but maybe from a UAV system. Yes.
That's fair enough. There's second question, which kind of I guess leads a bit on from that, which is, have you explored integrating it with LiDAR data to improve the resolution or accuracy, or is that something someone else or down the line thing for you to look at?
Okay. Unfortunately, I didn't have access of LiDAR data for this volcano, so I haven't done this, but would be interesting. Even though it's also important to remember that there are different kind of DMs. There are the DMs like the one that we used that was topography, consider also the height of the tree, while there are a system like the LiDAR that consider only the achieved directly the ground level. So if you compare probably ArcticDEM with the LiDAR, you also get a very high signal of topographic changes due to the trees if there are if you stay in vegetated area. So something of interesting also for other kind of application. But yeah, no, unfortunately, I haven't done this.
That's fair enough. It's a lot of work that you could do, I can imagine. Ian has a question kind of similar, following on from those, is what spatial scale of volcanic deposit need the high resolution of EarthDEM or similar? Have there have been previous studies that have shown 30-meter pixel, some ASTER and similar data sets can accurately quantify these volumes. So why do we need this extreme high resolution?
Well, I totally agree, but for example, just to show you the fact that, okay, there are some signals that cannot be detected from ASTER or however in general from lower resolution data. Because for example, just to show you, this lava flow, I think it would be very difficult to be detected from, and especially this one, because they have width of about 15 meters in most of the areas. So I don't think that you are able to detect from. Actually, I also have to say that I tried to get topographic changes from master for most of the Kamchatka volcanoes, and I didn't achieve to get nothing because they have a lot of artifacts in these volcanoes. So one of the other thing probably is this one. But however, there are a lot of unique signal that you got to lost from if you use lower resolution DM. For example, I don't think you are able to map the growth of a spine over this very narrow region here at the top, or other things. Okay, here I tried to study the lava dome growth of Cleveland by using both ASTER and SAR-TM and Copernicus. None of them have reliable topography within the crater of Cleveland, which actually they were just something like 3 or 4 pixels the whole crater. So here you see the difference. They have few pixels that cover the whole crater, and I have, I don't know how much, but they are a huge amount of pixels. So just to say that these lava domes cannot be detected from lower resolution DM because I've tried and I don't see nothing.
Yeah.
So yeah. So of course it's great to have a combination of them, but sometimes I show you also from Raunga that you got similar results. Other times, no, you need their resolution.
Yes, that makes sense. The really fine scale and details you'd miss out. So what are the key criteria you use to determine whether a detected topography change is significant or just within the error range? So kind of, yeah, those small details there.
Well, no, this is an important question. First of all, you need to see if there is any, if your signal is spatially related with the volcanic products. And to do this, for example, a lot of time we used also high resolution optical data to see if there is a match between the erupted products and the signal, because yeah, this is the first important thing. And then we have also to say that the vertical resolution of this DM, it's quite enough to map all the thicknesses of the deposits that I showed you, because all the one that I showed you have thicknesses higher than 2 meters usually. While when you go on lower thickness deposits, actually you don't see nothing. For example, here at what it was here at Pavlov, there was we had 3 eruptions, but I don't see any deposits any signals that is directly related to ashfall deposits. Maybe some of these positive signals, I don't know, but actually if you go to see, they are more related to areas where there could be some artifacts or other kind of things. So when we do not have any clear signal, also that is also related to the deposits that we can map, we don't use that signals because of course they detect everything, but then you have also try to figure out which one is true and which one is not true. And so sometimes it's very easy, other times it's not so easy. So we use it a lot, the verification with high resolution optical data.
Oh, that makes sense. There've been a few questions asking about kind of the softwares you're using. So one of them says you said that you're using a modified version of ICE to get the topography change. Is this open access for people to use as well, or is it something that you?
I'm not sure because it's a routine that was developed by one of the other previous postdoc here in Cornell by Francisco Delgado. I'm not sure if I made it open source or not, but I should ask it him. But well, definitely you can directly ask to him because, or however, we can share because we have the routine, we can share without problem. So yeah, maybe something that I can dig in detail if it's already has been already updated in some open source database or not, because actually I don't remember. But yeah, this is something of that however we can share without problem. So.
As people would be interested in trying it out for themselves as well, maybe. Bit more of a deposit question of how can you distinguish between melting ice from a magmatic deformation using remote sensing? For example, you showed some ice covered volcanoes. Is this something you can do, or?
Well, this is a tricky thing because, okay, now during the presentation, I didn't have time to show everything, but of course, when the lava flow in place at the above glacier, for example, we have 2 volcanoes in which it happens, Pavlov and Klyushevskoy. First of all, the thickness that we estimated are probably lower estimation, the lowest possible thicknesses, because it's possible that the lava melted part of the glacier, and so actually it was possible that the thicknesses of the lava flows was higher, but we estimated the lower thicknesses because we had a reduction in the level of the ground. Even though there is an article at Pavlov that say that for the 2013 eruption, they observed no changes in the height of the glacier above which the lava emplaced, probably because the carapace of the developed in the lower part of the lava flow prevent a huge amount of melting of the glacier. Then there are other cases like at the volcano, which on the contrary, we had a huge amount of melting, and so we detect negative topographic changes. So, but as for the deposits, what is interesting is that you can use this DM to calculate the melting of the glacier, as in these cases, for example, or when are available. Now I don't have. Maybe let me check if I have an example from Pavlov here or not, because I don't remember. But yeah, you see that what the other thing that you can do is to map these distal large deposits that mainly are related to all the materials that was remobilized by the water that was melted during the eruption. So these are other kind of deposits that you can map directly. Yeah.
That's neat. So we have a question here from Eva, who says, great talk. A question with respect to the use of the bistatic TanDEM-X data. Have you experienced any offsets with respect to the pre and post event DEMs that you do suspect come from other sources than the geocoding error, such as baseline estimation areas?
Well, to be honest, no, because for example, now I haven't shown, but for Raung data, I have a lot of bistatic data, also with different kind of baseline, and all of them matched very well. So the only thing that I have is probably this shift that was actually for me it's a geocoding error. While actually, yes, maybe we have seen very small changes in the age changes because you know that the age of ambiguity is directly related to the baseline. So there are effects in the estimation, but actually, well, they were not so important, but maybe they were not so important because in this case we had a very important age changes. Maybe if you go on the scale of age changes of, I don't know, 1 meter, 2 meters, 3 meters, probably you start observing differences that became more significant. So yeah, I haven't done an in-depth analysis of this, but yeah.
She also goes on to ask, so you mentioned that you use the DEM co-registration tool for your optical data set. Did you use these kinds of tools to correct for potential offsets in the InSAR derived DEMs as well?
Well, I haven't done. The problem is that in this case at Raunga, it's quite known that when you have a very huge amount of topographic changes, you can have that kind of geocoding error. The point is that to correct this kind of geocoding error, you should geocode with respect to a correct DM, which in our case could be the post-eruptive EarthDEM. The point is that I was when I did this article, I was more interested to see the errors that we can get if we don't have the solution. So if we don't have another high resolution DM that already show us which was the correct topography. Also because we were able to have access to this ArcticDEM, the post-eruptive EarthDEM, just after that we had processed all this InSAR data. And so at the beginning we thought that it was through edge changes. So we discovered that it was a strongly edge changes in this area just when we had access to this DM. So something that no, but probably we haven't done, but probably we would achieve to correct these geocoding errors. So the problem is that often you do not have other high resolution DM with respect to which you can correct the geocoding errors. So it's good to note that when you process bistatic data in very steep areas, there could be some geocoding errors. So that affects also the changes estimation. So this is the point.
That makes sense, yeah. We have a comment here from Federico saying, excellent talk. With regards to Samaru, he would just like to point out, like to suggest bearing in mind that the volume estimates derived from a rover tend to overestimate the volumes calculated from DEM differencing, as they are associated with significant uncertainties. So this is a pattern that has been consistently observed at Stromboli, where volumes derived from topographic change detection usually fall between the mean and the minimum values estimated using data. So something you've asked before, I guess.
No, yes, it's something that we also have investigated. First of all, Semeru is a volcano from which the relationship between VRI and the volume of lava works much better than Stromboli. And the other thing is that, and this was also the reason of why we associated a much higher error, because we associated an error of the volume of about 50%, while usually when you calculate the volume from Mirova data, and you can directly estimate the CRAD parameter from other data, like in our cases, usually the associated error is of about 20%. But however, we wanted to be much more conservative, and so we associated the highest error of 50%. But what it was also the other thing that was important for us is to show that we know that that is just a first order quantification of the volume, but for volcanoes that are not so well monitored, I think that is something of important because, for example, even though it's not so precise, right now you can try to estimate directly from Mirova in near real time the volume of erupted lavas, thanks to the fact that we calibrated the CRAD. We are also aware to the fact that the CRAD parameters can change inside the same volcano if it changes the composition. So it's not something of static. But however, when you don't have so many data, we believe that is something that can however improve the volcano monitoring. So yeah, we are very aware about the fact that there are a lot of limitations, but however, it's something that if you don't have other kind of data that can be used, it's something that at least you can use.
Yeah, it's better than nothing, definitely.
Yeah.
I'll wrap this up. There's one question I'll end with is, have you considered what other topographic elevation models you would like to continue or experiment with in your research? So what's next for you, kind of thing?
Well, actually, I don't know, because this is a project that is just ended, and so I don't know which will be the next step. Actually, we wrote a couple of proposals for which we would like also to have access to other kind of high resolution DM from Airborne and other system. But yeah, we'll see if the proposal will be approved or not, and if we will have access or not to this other kind of high resolution models. Something like, but I think that it's something that it's very important because having updated the high resolution DM is important for the geodetic community. So it's definitely
Yes, I think
something
everyone
important. Yeah.
up-to-date DMs is, I think, something everyone can agree on is needed. So we'll end it there. There are a few other questions, but I assume also Federico would be happy if anyone contacts him down the line if they're interested in talking in more depth with you. So thank you again for a great talk and answering all those questions. There won't be a webinar in June, but we'll be back in July and we'll share that information about that session closer to the time. So thank you again for everyone for coming and listening.
Thank you. Bye.